We began our study of Earth science by looking at our entire solar system, from the sun to the Kuiper Belt and everything in between. Then we zoomed into planet Earth, diving through the layers of our atmosphere, exploring the weather phenomena that occur there. We'll continue our journey through Earth's layers by tunneling down until we reach the core. Many of you learned a bit about Earth's inner layers in elementary school, and will continue to add to the complexity of that knowledge this year. For the next few weeks, we're going to put on our geologist hats. Geologists are scientists who study the forces that make and shape Earth. They use the observations they collect to search for clues about Earth's history and its future. How did our Earth form? What will it look like in 100 years or 100,000 years? The forces geologists observe fall into two categories. They're either constructive forces, meaning they construct or build up features, or they're destructive forces, meaning they wear away or destroy surface features. Surface features are things like mountains, volcanoes, plateaus, and the like. Currently, we observe that there are seven giant land masses called continents made up of layers of rock surrounded by oceans. But as we'll see throughout our journey, Earth didn't always look this way, and it won't look the same in the future. So, how do geologists know anything about the layers of Earth? Can they really drill down to the core? Sadly, no. As much as I love the movie Journey to the Center of the Earth, it's a work of fiction. The deepest man made drilling hole on Earth is in Russia. It's called the Kola Super Deep Borehole. It's about 7.5 miles deep, about a third of the way through the 22-mile thick continental crust. This sounds impressive, and it is, but you have to keep in mind that this borehole is made by a drill and is only about 9 inches wide, so humans can't go down there. Even if they could, we wouldn't survive, as temperatures that deep are upwards of 180 degrees Celsius, which is about 350 degrees Fahrenheit. You'd be cooked. So, to gather data, geologists have to rely on indirect observation. They use energy waves called seismic waves made by earthquakes to learn about the structures of Earth. When the Earth rumbles, it generates these energy waves, much like a rock hitting a pond makes rings of ripples that move outward. Have you ever noticed what happens to one of those water ripples if it runs into a rock or other obstruction? It changes shape and changes its path, right? The same thing is true for seismic waves. When they travel through the layers of Earth like water ripples, they change their path when they run into a layer that's made of different materials. Energy travels differently through liquids than it does through solids. By taking careful measurements, scientists are able to calculate the depth and thickness of these different layers. Pretty neat, huh? Some scientists are also looking at some direct observations from meteorites that fall to Earth as they were once molten, as well as some other small pieces of information. But most of our information comes from seismic waves. Because of all of this data from geologists, we now know that Earth has very distinct layers with very different conditions in each layer. We'll look at each of these in detail, but there are two generalizations that we can make. The first is about temperature. You've probably noticed that on a hot summer day, when you dig your feet down into the sand to keep them cool, it is cooler down there. Or maybe when you were little digging in your backyard, the ground below the surface is cooler. However, this changes dramatically after the first 60 feet or so. After that, the temperature rises consistently about 1 degree Celsius, almost 2 degrees Fahrenheit, for every 30 meters down that you travel. My classroom is about 15 meters long, so think about digging down twice that distance, and the temperature will rise 1 degree Celsius. Room temperature is about 23 degrees Celsius. So after digging for a mile or 1600 meters, you'd increase your temperature by about 80 degrees Celsius, which is about 175 degrees Fahrenheit. Pretty toasty. The second observation we can make about traveling through the layers is that pressure increases as depth increases. Just like we talked about with atmospheric pressure, the lower you go, the more air pressure you experience. The same is true as you tunnel down through the layers of Earth. Keep both these factors, temperature and pressure, in your mind as we continue on this journey. So let's take a look at these distinct layers. Many of you learned in elementary school that there are three layers of Earth: the crust, the mantle, and the core. And this isn't wrong, it's just a bit oversimplified, which is perfectly appropriate for early learners. But now that we're super cool, sophisticated, and awesomely brilliant middle schoolers, we're going to add a layer of complexity to what we already know. So let's look at these three layers: the crust, the mantle, and the core, and see what other features are actually there. So we're standing here on the surface of planet Earth, ready to tunnel down through our layers. The very first or outermost layer is called the crust. It makes up all of the mountains, soil, and ocean floors. It varies in thickness from the thin ocean floors coming in at about 5 kilometers thick to the tallest mountains that are about 100 kilometers thick from their foundation to their peak. Continents and other land masses are made of continental crust, which tends to be thicker but less dense and contains certain kinds of rocks like granite. On the other hand, ocean floors are made up of oceanic crust. I know, we're very clever with our naming. As you can see in this illustration, oceanic crust isn't as thick as continental crust, but it's much more dense. Think of the weight of all of the water above it, squishing it down. That's a lot of pressure. An oceanic crust is made of different kinds of rock, like basalt. That means that it likely formed in a different way than continental crust. We'll talk more about that soon, but for now, let's keep digging further down into our next layer. The mantle is below the crust and is actually split into different layers. The thin, rigid upper region of the mantle is called the lithosphere, and just below that is the asthenosphere. The rest of the mantle, which lots of people think is liquid, is actually solid. It's sometimes called the lower mantle or mesosphere. We'll talk more about those in a bit. Let's continue digging through our mantle down into the core. The core, much like the mantle, is also made up of layers. It has two distinct layers called the inner core and the outer core. Earth's core makes up about a third of our total mass, but way less than a third, about 15% or 1/7 of Earth's volume. That means that a lot of mass is shoved into a very small volume, so Earth's core is super dense. It's made mostly of iron and a little bit of nickel thrown in there too. Having that outer core is super important in making our magnetic field, which you may remember from our unit on astronomy, is responsible for deflecting a bunch of solar wind and protecting our atmosphere from being blown away, like scientists believe happened on Mars. So let's recap really quickly. This is a diagram of what many of you came here knowing. Three big layers. Pretty straightforward, right? Wrong. Now we know that it's actually much more complex than that. So now that I've ruined your childhood and made you question everything you thought you knew, let's do a little side-by-side comparison. This is my favorite diagram. Take a look. Now really look at it. On the left, we can see our old understanding of Earth's layers. And on the right, we can see our new understanding. Earth is made up of not 3, but 5 distinct layers. The outermost layer is the lithosphere. It's the rigid or rocky layer that incorporates all of the crust, as well as the uppermost solid portion of the mantle. Below that is the flexible asthenosphere. The mesosphere, aka the lower mantle, comes in next, with the outer core below that, and finally the center of the Earth, which is the inner core. Now that we have our mind set right, let's look at these 5 layers in more detail. Lithos is Greek for rocky, referring to the rigid or hard nature of this layer. It's made up of the crust, both oceanic and continental, as well as the rigid or stiff upper part of the mantle, and it's divided into about 20 tectonic plates. Later on, we'll explore these tectonic plates and look at how their interactions help create and destroy different features across Earth's surface. The asthenosphere is probably the least familiar layer to you, but it has a super important job. It's the layer that the tectonic plates sort of float on. It's got a funny name which actually means weak sphere in Greek. It has nothing to do with its strength, but rather the flexible and fluid like nature. Think of it as the opposite of rocky. Sometimes geologists call this quality plastic. Think about a piece of floppy plastic like a page protector. Could you easily change its shape and contort it? Yes, right? Easy. But that's because it's weaker or more flexible than something like the rock that makes up the lithosphere. It's a solid, but more like frosting. It flows very slowly, heated by the convection currents in the mantle. Remember that the molecules in a solid still move, just much more slowly than a liquid or a gas. This movement causes the plates to move, which in turn cause events like earthquakes, valleys, and mountains to form on the surface. So, this weak little layer is responsible for quite a bit of construction and deconstruction. This diagram is merely illustrating the scale of each of the layers. In the larger picture of Earth, you probably can't even see the thin yellow line that represents the crust, that top part of the lithosphere. But if you look at the zoomed in section on the left, you can see that light gray area and the yellow area represent the lithosphere. Below the lithosphere is the asthenosphere, which is about twice as thick, and then the large mesosphere, which makes up the bulk of the rest of the mantle. As you can see from the scale model on the left, the mesosphere, or lower mantle, is the thickest of the 5 layers of Earth. Meso is Greek for middle and was named such because it's the middle of the 5 layers. Does anyone remember where we have another mesosphere? If you said our atmosphere, you're right. Our atmosphere also has 5 layers, and the middle layer where was also named the mesosphere. Below the mesosphere is the outer core, which is mostly made of molten or melted metals, specifically iron and nickel. They behave like a very thick liquid, which we call a viscous liquid. Picture molasses or honey. Those are very viscous or thick, as opposed to water, which is not very viscous or runnier. This is due to the extreme temperatures, upwards of 4,000 degrees Celsius, which melts the metals into a liquid state. The inner core, however, has these same metals, iron and nickel, but they exist in a solid state. It's about 5 to 7,000 degrees Celsius at the center of the inner core. So how can it be hotter and the metals not melt? Do you remember at the start when I told you to keep 2 factors in mind? Those 2 factors were temperature and pressure. Pressure is the culprit for this phenomenon. As you get closer and closer to the center, the pressure increases, so much so that it forces all of the molecules to squeeze together so hard that they become a solid. So even though it's really hot, the pressure is so intense that it keeps the metals in the inner core in a solid state. One fancy feature of the core that of Earth is the generation of our magnetic field. Scientists used to believe that it was the iron inner core that was responsible. However, we now know that iron loses its magnetic properties with temperature as high as those in the inner core. It's actually the outer core that is responsible for our amazing magnetic field. It's called a domino effect. Flowing liquid in the outer core generates an electric current. The rotation of Earth on its axis causes these currents to generate an electric field covering our planet. It not only deflects destructive solar wind from our atmosphere, but also helps us navigate the world using compasses, which use an internal magnet to detect Earth's magnetic field and point north. And there we have it, the 5 layers of Earth, from the rocky lithosphere to the flexible asthenosphere, the solid mesosphere, molten outer core, and finally the solid inner core. Next, we'll take a look at how interactions and processes within these layers help to form, destroy, and reform the features across Earth's surface.